Okay, so today we're going to start to formally put together the first half of this unit, which is talking about momentum and something called impulse. Next class, we are going to build up to the point where we can talk about collisions. But so far, okay, we're only really focusing on linear momentum, meaning one-dimensional momentum, and impulses. We'll find out how closely related that they are. We could take a much more expanded version of this and talk about two-dimensional stuff. We can do three-dimensional stuff. But truth be told, I think we kind of understand the basics when we get to one-dimensional stuff, and we really could, if for some reason we had extra time, then just take those simple understandings and then apply that to other dimensions. But, okay, in the preceding chapter, meaning what we had just covered, which is work, power, and energy, as well as Newton's laws, okay, some of the situations that we were trying to describe, okay, were a little too difficult to do just simply in terms of Newton's laws. Like, think about roller coaster problems. If you had to try to analyze that just from the lens of Newton's laws, only focusing on net forces acting on mass, the acceleration on different points, truly in the three dimensions that would have been for a real roller coaster problem, that's a pretty complex way to try to describe what's going on. Work, power, and energy, and the energy approach that we took gave us some tools that we could use to kind of dissect how we can deal with some of those problems. Our goal in this unit is to give us another tool in our toolbox, and hey, certain things we can dissect from a momentum perspective so that it's a little bit easier for us to solve. Could we do it during an energy stance? Maybe. Could we go ahead and do that from Newton's laws? Maybe. Going back to even our formative question that was posed to us, we could do that from an energy standpoint. Okay? But no, if we're going to rewind all the way back to Newton's laws, Newton himself, when he was talking about his second law, the one that we now talk about as force, mass, and acceleration, Newton himself actually wrote that law talking about momentum. And that the momentum of the object would be rigidly maintained, not acceleration. Okay? So that's kind of where we're coming full circle with this, and truly, okay, Newton himself envisioned this as a discussion about an object's momentum. Now, momentum is very, very simple to calculate. It is defined as the product of an object's mass multiplied by its velocity. So yes, we actually use the same two things to calculate it as we do with kinetic energy. Okay? Mass, velocity. However, it's not 1/2 mv squared, which in energy certainly gives a disproportionate amount of energy to an object's velocity. The more velocity it has, okay, we have that squared as part of that equation, it gives it that much more energy. However, with momentum, it is simply just mass times velocity. Quick thing about physics land, we ran into a little small issue with momentum, and that was the variable at which we were to use for it. Okay? Couldn't use the lowercase letter m, could we? Why not? We already have that used in mass, and especially since momentum requires mass as part of that calculation. In physics land, and we have chosen the lowercase letter p to represent momentum. Clearly because you can see the letter p in momentum. Everybody sees it, right? Sure, if you squint to the point you actually don't read any letters, maybe you can actually see the p. But, okay, p it is. Okay, that's what we do. Just a friendly reminder, we see the arrow notation, which means what? Something we haven't seen in a while. It's a vector. We have to have the three things we need for that. Number, unit, and direction. Okay? We use derived units for momentum. Okay? What are the SI units for mass? Kilograms. What are the SI units for velocity? Meters per second. And what do we get when we multiply one by the other? Kilograms times meters per second. Okay? And a lot of times when I even write it out, okay, it'll just be literally kg times meters per second. And that's perfectly fine. And those would be our units for momentum. Okay, if the net force acting on a singular particle is 0, there's no acceleration and therefore no change in velocity. Okay, that means that the momentum of that singular object remains constant and it is conserved. So sometimes we will start talking about the law of conservation of momentum. But frequently, whenever we're talking about the law of conservation of momentum, and the first part of what's stated here is very important, states that whenever two or more particles are going to have a momentum interaction, that means that the total momentum is going to remain constant. Kind of like the law of conservation of energy. Okay, we just had that kind of changing forms for that singular object. With the law of conservation of momentum, we'll kind of talk about the total momentum of that system is going to remain the same. It's just whether that's going to be as part of one object or many objects within that system. Okay, that's momentum. Okay? What's more important to me, even though momentum is very, very important in physics land, is this concept of impulse. And we're going to have its connection to momentum in just a minute. Now, impulse, there's a good chance is something, scientifically speaking, that you have not heard about before. Okay? And it is when a force acts on an object over time. It imparts an impulse. Now, really, this is what we've been talking about all year ever since we introduced the concept of force. Okay, a force being applied over some sort of duration of time. I know we know this by now, but what are the SI units for force? Newtons. SI units for time? Seconds. Okay? And it also has that derived unit of Newtons times seconds. And that's it. That's what impulse is. Okay? As we've already seen, when a net force is applied to a particle, its momentum is going to change. Think about this before we hop over to the next page in our note packet. Think about this going back to Newton's laws. Newton's laws, we said a net force applied to some sort of mass-provided acceleration. Again, kind of putting it in the sense of what Newton himself thought. Newton was just thinking simply that net force applied to an object is going to have a change in that object's momentum. Now, here's what's important about this. Okay? Impulse, okay, of the force acting on a particle equals the change in momentum of the particle caused by that force. And it is what we put together as the impulse momentum theorem. Now, what you see on the board are four equivalent values. Impulse, which is capital letter I, it is equal to the change in momentum, which is also equal to a force multiplied by a duration of time, which is also equal to mass times a change in velocity. Now, why are we showing four equivalent values up on the board? Because depending on the situation that we have, we might need to use any two of these. So could we set impulse equal to m delta v? Absolutely. Can we set m delta v equal to our change in momentum? Yeah. Can we set m delta v equal to f delta t? Yes. Any of these values we can set equal to each other, depending on the information that we have, to kind of figure out what's going on with it. Now, the interesting thing about impulse, we'll kind of get into a little bit more as we kind of get into the sample problem. Because I think that there is an important connection for us to make with momentum and impulse. Okay, so let's go ahead and let's jump right into sample problem A. A 30,000 Newton truck is traveling 50 kilometers per hour east. Okay, we have a couple of things that we are going to find. But before we do so, you are well-trained physics students at this point. There are a couple of red flags that should pop up. What's one of them? Kilometers per hour, kilometers per hour, depending on how you would like to state that. How do we go ahead and convert that to what we need? First off, what do we need to convert it to? Meters per second. Okay, so what do we need to multiply by for kilometers per hour? Multiply by 1,000, divide by 3,600. Please go ahead and do so. And Matt, when you have a response, let me know. It is what I got. Is that what everybody gets? Okay. We get 13.889 meters per second. It is east. For right now, let's just kind of leave it at that. Because again, keep in mind, we do have to take into account direction with this one. Anything else that stands out to you as what's wrong?
The traffic should have a mass.
Good. In order for what we need, don't we need a mass out of all of this? Yes. Trick question, but not really. What is 30,000 really? What value is it? It is the truck's weight, just expressed in SI units. As opposed to us in the English Standard System expressing that in pounds, that's just expressed in the SI system. So how are we going to work backwards from a weight in newtons to a mass in kilograms? Just divide by 9.8. So 30,000 divided by 9.8. Justin, when you got it, let me know.
3,061.224.
Bananas, monkeys, gallons of milk.
What is
That's a good question.
Kilograms.
Kilograms.
Thank you, Gila.
So, okay, 3,061.224 kilograms. Everybody agree that now we have things at least in SI units? Okay, I hope so. So, let's start off with the simple stuff now. Now we can find the momentum of this truck. So P for momentum is equal to what? What's the equation? P equals mv, just mv. The delta v is for something else a little bit later. Okay. So when we go ahead and we take a look at that, well, this now becomes a very simple plug and chug. 3,061.224 times our 13.889. Go ahead and solve for the truck's momentum at that point. Natalia, what do we get? 42,517.34. Absolutely. Okay. 42,517.340 kilograms times meters per second. How, if at all, would this change if this was traveling west? Would it? How, if at all, would that change if it were traveling west? Anything? Would it change? Or is Talbot playing mind games again when he's very good at it? Well, I know, so I want you to see if you know what's going on. I know what the answer is. It'll be negative. It should be negative if it were traveling west. Because again, remember, the velocity component that we're basing this off of is a velocity. It has a value that has a direction expressed with it. Okay? And if we're assuming that we're traveling along an x-axis as east-west, okay, yes, absolutely, that would turn into a negative. It isn't, because it is traveling east, so we'll just leave that as positive. Okay? All right. Now, we're asked to calculate in part B, to calculate the impulse imparted on the truck if it brakes to a stop in 35 seconds. Now, thanks to the impulse momentum theorem, we have several different ways in which we can do this. I don't want you to write anything down just yet other than I equals, and let's kind of talk about this. could we do I equals F delta T? What force would you use? And that would be a catastrophic mistake. And that's why I'm bringing it up here. Because the question I would follow that up with, is that the force responsible for stopping the truck? No. If we knew that force, could we then do F delta T? Absolutely. But we don't know that force. And that's why this kind of allows us to deal with certain things that the application of Newton's laws really wouldn't. Okay, so we don't have to have that force, and we can still get where we need to be. Now, could we do M delta V? Well, we know the mass already. Do we know the velocity change? Yeah. It's going at some speed. It stops. So what would the delta V be? Negative 13.889. Okay? So that's one way in which we could do it. Also, could we do the change in momentum? Yes. It has that momentum at that speed. What's its final momentum going to be? 0. Okay? Now, I'm going to do it this way just to kind of make a point, because we technically could do it one of those two ways, but we kind of have to vet the process to make sure that it works. I want to do M delta V just because I think that's one of the ways we will more commonly do this. Okay? Now I know we still have the same mass, 3,061.224 kilograms. Okay, our velocity change, because remember, be final, 0, minus initial, 13.889, negative 13.889. Please do not touch your calculators. What's our answer going to be? Negative 42,517.340 monkeys, bananas, gallons of milk. Correct. Newton seconds.
Obviously not.
Now, and here's the thing. Impulse, I'm going to stress this again. Impulse is equal to a change in momentum. That's really how it's defined. Okay? But it is the change in momentum, not the actual momentum at a given point in time. Okay? So, because we're coming to rest, okay, think of it this way, kind of the truck is losing its momentum, so the impulse imparted on that has to be a negative value based on what we had. We had some momentum that was positive, okay, now we've brought to the point where it is negative. Now, part C, calculate the force necessary to stop the truck. So, correct me if I'm wrong, which I'm not. I equals F delta T, correct? Okay, well, we now know the impulse, we now know the duration of time from the previous step. Can we work backwards to figure out what that force is? Yeah, so what is the equation? F equals I over delta T. Okay, so negative 42,517.340 all over what duration of time? All over that 35 seconds. Please go ahead and solve for the force responsible for stopping that truck. That's where we use it right here. We didn't use it in the previous step. It was extra information for what we needed there. Also so I can trick you and get you to think that you may use that 30,000 newtons. But remember, what information do we need? We need the force, in this case, responsible for the impulse. The force responsible for stopping the truck. Okay, so the 42,517.340 divided by 35. And what do we get, Jake?
Negative 1,242.7.
How many of you, how many of you would agree by show of hands that that's what we should get? Good, we should, okay? And that is the force responsible for the truck. Is the 1,200 newtons a very different value than the 30,000 newtons that we had previously? Absolutely. Okay? So, I think pretty straightforward in sample problem A. Now, real quick, is any of this math terribly difficult?
No.
I hope not. Okay, this is probably about some of the easiest computational stuff we're going to do all year. Okay? But, as we're kind of prodding earlier, make sure we have to have the right information plugged in at the right points. Okay? Just be processing what it is we're doing before we go ahead and do that. Okay? So, here's what I'd like for you to do. Go ahead and solve sample problem B on your own, and please stop at sample problem B. Do not go on to sample problem C. Okay, so let's take a quick gander at what we have up on the board. Part A, what is the car's change in momentum if its mass is 1,500 kilograms? Now, Michael, I do need to state, the change in momentum is fine if we do P final minus P initial, but you're going to have to kind of spell that out a little bit more. What I would probably suggest doing is, because it's what you'd end up doing anyway, delta P equals M delta V. Set those two equal to each other, and it's probably effectively what you did. Is then going to be our 1,500, okay, multiplied by final velocity, 67 minus our initial 25. We'll still probably get to the same point. Do we get 63,000 kilograms times meters per second? Nice, easy calculation, hopefully. Okay. Now, what is the impulse? Okay, imparted on the car to cause this acceleration. Now, notice part A of this asked us straight up for the change in momentum. That becomes really easy to do. Okay. Especially if we've kind of done that in the previous step, and Kendall and others, I'm okay with us saying I equals delta P. We just solved for it in the previous step, or we can reaffirm what we already know, and we'll get to 63,000 Newton seconds. Okay, part C of this, though, is the question that I want to get you to think a little bit, and this does not require calculation. It does require some brain cells. If the time required to accelerate the car shortened, would the impulse increase or decrease? Think about that for a second. Please do not provide a verbal response. The time required to accelerate the car shortened, would the impulse increase or decrease? Alex, what do you think?
I think it would remain the same because it's the change in momentum. And the change in momentum would be the same. So I don't know if that's exactly it.
Okay, can I counter that with something? Just as part of an intellectual discussion? Okay, so we're shortening the time of which that this is going to happen.
Yeah.
So what do we tangibly have to do in order to shorten the time frame over which that happens?
Increase the force.
Absolutely. We have to increase the quantity of force in order to make that happen. So wouldn't that change your impulse?
I don't know. On my paper I wrote that it would decrease because I equals F delta T. And then when T gets lower, but then I realized the force has to be higher for this change.
And by the way, you're absolutely correct. It doesn't change the impulse. Okay? For the exact reason of what we're talking about. And when we decrease the time over which that same event occurs, notice how we're still going from the same speed to the same speed. Even though we're shortening the time, we offset that by a larger force in order to make that happen. That doesn't change the change in momentum. Okay? We're still going to have the same initial momentum. We're still going to have the same final momentum. We've changed the parameters of which how we got from one to the other, but the impulse itself would remain the same in that instance. So often when it comes to some of this stuff related to impulse, we often talk a lot about the interaction between force and the duration of time over which that force occurs. Now, we are going to get to sample problem C in a second, but I want to have a little bit of a chat before we get there. One, I'm going to give a little bit of a precursor to this. Yes, we are going to dissect some data related to a very unfortunate and fatal car crash. I'm realizing that most of you probably don't remember 2001. But actually about this time of year is when NASCAR has their Daytona International race for NASCAR, and unfortunately in 2001, Dale Earnhardt Sr. Was killed in a car accident with that, and the primary purpose for his injuries were because of impulse-related things. This is kind of what I want to talk to you about as a precursor to this problem. I hope that you understand, okay? When you, specifically talking about cars, and more maybe the consumer cars, the things that we drive on roads, okay, there are a lot of considerations that are made in terms of safety. There are probably lots of things built into your cars, features in your car, that you don't even know about, and they're done on a safety perspective. When you get into a car crash, and let's kind of say it's a certain type of car crash, let's say you hit a stationary object, just because it's going to help us kind of talk about the scenario a little bit easier. Okay? You have some speed before the collision, your final speed is 0. Okay? Same for your car, same with everything that's in your car. Now, as you sit in the driver's seat of your car, there are several things around you that help with collisions. What's one of the things that can help you in a collision? An airbag. If you're in a seat that has an airbag in it, which every single modern car certainly has, especially for the front occupants, what does an airbag do? Let's look at the physics behind what the airbag does. And yes, I know when you get into a collision, it inflates in front of you. And by the way, how many of you in here have actually been in the seat of a car when an airbag has deployed? Is it a comfortable experience? No. Okay? You know, I remembered when airbags were starting to kind of become a thing that was a standard safety feature for a lot of vehicles. And they'd show them a lot of car commercials of like the slow footage of the airbag, you know, deploying, and it kind of looked like this comfy little pillow that you can go ahead and rest your head on. It is not a comfortable experience. Yes, very much so. Okay? But what's happening in that very short period of time makes a huge difference to your safety. Okay? And you need to know that it is, thankfully, over-engineered to make sure that it happens exactly. Because that airbag deployment has to happen at the perfect moment in time. Because if it doesn't, it can actually be a bad thing in an accident. Okay? But what does an airbag do in terms of impulse? What it does is it actually lengthens the time that you collide with your car. In the olden days I say even well before me, okay? Let's pick a time frame of like the 50s and 60s, okay? A lot of car parts were just made of very hard plastic, metals and things like that. Steering wheels were just stamped steel with a little bit of plastic trimming on it, okay? If your body hit that, it happened in a very short period of time. Now you had the same momentum change as everything else, okay? It just happens that it applied in a very short period of time. So what does that mean in terms of impulse? Impulse stays the same, short amount of time, force goes way up. Okay? So the force imparted on you was pretty significant. And if you're in this kind of car crash, where let's say a frontal crash, so your momentum is carrying you forwards, there actually are 3 collisions that occur. 1, your car hitting whatever object it is that it hit. 2, you colliding with your car, okay, if that was you hitting the steering wheel or even the restraining, seatbelts and things that you have. And the third and final collision, which is the most important, is your internal organs hitting the front of your body. And if it was a very high amount of force imparted on you, and that is affecting your internal organs, bad things can happen. So what the airbag does, okay, is it lengthens the time at which you are colliding with your car. Even if it's only by fractions of a second. If we can double the amount of time over which that occurs, what happens to the force? It's cut in half. So what used to be very small amounts of milliseconds, and we're still only talking about milliseconds, okay? We are talking about trying to lengthen the time over which that collision occurs. And by the way, it's not just your steering wheel, okay? What a lot of you may notice, maybe the next time you get into your car, your steering wheel, your dashboard, the top of it, and the under part where your knees are, I want you to try to get in your car and see if you can kind of push on it. What you will notice is, in most vehicles, to a certain degree, there's a certain level of sponginess to it. Okay? It's got a little bit of give to it, and it should. Okay, now it's not going to be, again, some comfortable, fluffy little pillow just kind of sitting on top of your dashboard. Okay? But it's done that way on purpose, because especially in your footwell, okay, if your knees are colliding with your dashboard, there needs to be a little give to that. So again, it helps to limit injuries to your body as you are coming in contact with your car mid-collision. Okay? So from a safety standpoint, a lot of the things designed around you as the driver and other occupants in your car are specifically designed to increase the time of collision between you and the vehicle that you're in. Okay? I was in a very serious accident years ago that I'm actually very fortunate to have walked away from. And it was in part due to the safety features of the car that I was driving at that time. Okay? I was actually driving on the highway, and someone was in the fast lane, okay, to my left. They decided, this was in the early 2000s, and CDs were kind of still a thing back then. They decided that at the time that they were trying to pass me, they were going to reach into their passenger footwell to grab a CD. At the same time they did that, they pulled over on their steering wheel and clipped the rear corner of my car at highway speed. Spun around several times, went through the guardrail, and flipped several times off the side of the road. And I was very fortunate to have walked away from that accident. Certainly a couple of cuts and bruises, but airbags, all the other things that are in the car to go ahead and make you safer. Certainly I'm a living testament of the fact that it works. Okay? And I hope that no one in here has to test those theories. But do know that a large part of what you have around you, and you might not even be fully aware of, they certainly are there to help you. Now, what's most important? Preventing the accident in the first place. Okay? But a lot of times those split-second decisions, split-second things that can happen, okay, are sometimes out of your control. There's nothing I could have done to avoid that collision. Believe me, I've run myself through what I could have done differently. And I'm also very fortunate that I was the only passenger in my vehicle. But, okay, that's what can happen. Now, let's bring it to sample problem C. Okay? So, I hope that you understand, in just about every form of automobile racing, the goal is to make a car typically as light as you can so it can go fast. Okay, the lighter it is, the faster it can go. And even in NASCAR, which doesn't, well, they do have a lot of regulations, but at the time they did not have a whole lot of safety regulations. You have cars routinely going 200 miles an hour plus with nothing but basically a bird cage around them. Okay? It's a safety real cage, but you know, that's what it is. Okay? There's no other real safety features that are in that car, especially in this era. And part of the reason why I bring about this accident is because there also spawned a generation of safety improvements around that time frame. And really started to springboard into discussions, not just in automotive racing, but other forms of just general passengers and vehicles. So, in 2001, Dale Earnhardt's 1,545 kilogram car crashed into the wall at Daytona International Speedway. In doing so, Dale experienced a velocity change at negative 19 meters per second for a time of approximately 80 milliseconds. And that 80 milliseconds is just simply a metric conversion, just like we do millimeters to meters. Okay? Here's what I'd like for you to do. On your own, I'm going to ask you to go ahead and solve parts A, B, and C for this, and then we'll have a quick chat. Okay, so let's take a look at where we are with part A. and we're asked to solve for the car's momentum change. And again, please be careful with the wording of things. This is momentum change, so everyone should have delta P equals, and then probably based on the information we have, definitely M delta P, which gives us a change in momentum of negative 29,355 kilograms times meters per second. Okay. Here's the good news. Okay, and then for part B, when we are doing impulse, it's okay. I equals delta P. We know what it is. Okay, we can just go ahead and put that there as well. Okay, so I equals delta P, also negative 29,355 Newton seconds. Now, to go ahead and calculate the force, a lot like with what we did before, okay, we know the impulse. We can then take that, divide by the duration of time, which when we convert it is 0.08 seconds, which is negative 366,937.5 newtons. Now, I want you to kind of think about this for a second. 80 milliseconds. I want you to take one Mississippi in your brain and cut it into 10 equal parts. Whatever 10 equal parts of one Mississippi would be. And in less than one of those 1/10 of a second, you'd have 367,000 newtons of force applied to that vehicle. I would consider that to be significant. I think you would too. Okay? And there is an important lesson to take from this. Okay? And it absolutely is about driving safely. And even though these are race cars obviously designed to go very fast. I'm personally not a big fan of NASCAR, but there still is a strong lesson to take from it. Things can change in a fraction of a second. Okay? And it only takes that fraction of a second to be in some sort of trouble where an accident can occur. Now, 19 meters per second velocity change, okay, is very possible here on our public roads. This is not like that this is some extreme quantity of speed. But I know from driving around outside that some of you drive faster than that in our school parking lot. Okay? So keep in mind that there are things that we probably need to consider, the long-term consequences of what could happen if something were to occur. I'm not asking you to drive so defensively that you're afraid of anything happening, but at least be processing that things could happen at any given moment. Now, in motor racing, there's actually some very significant changes that came after this. Notably is a very specific device called a HANS device. And actually, as part of what happens is your neck, both your muscular system and your skeletal system, can only handle certain quantities of force in certain directions. That if you exceed a certain value, basically your neck muscles cannot hold your neck together. And that's unfortunately what happened with Mr. Earnhardt in this accident. And that the forces were just so extreme on him that probably was something pretty quick. But for us, so in the racing world, they have this device now, and again, it's designed to help, but will not certainly solve all issues. But they actually wear a device that kind of goes under their harness, that they literally have tethered straps that go from their helmet down to this device that help to kind of save some of the load, some of the force that's experienced by the neck in some of these incidents. So, and that, there's no true telling as to how many lives or injuries that would have helped prevent, but certainly has done a lot of significant things in the auto racing industry, and put a lot of things into perspective about safety in general. I know you guys are now at an age where that's kind of not necessarily your reality, but back in 2001, it was. All right.